Next, we're going to look at Java code for solving the Maxflow problem. This is the most complex graph processing algorithm we've seen so far, but it's a relatively small amount of code that builds upon the mechanisms that we've been studying for the last couple of lectures. Now the graphs that we're working with are a little more complicated because we have to associate with each edge not just a capacity but also a flow. So we'll build a slightly more complicated data type for edges called a flow edge, where for each edge we can keep track of that information. So we not only have to keep the from vertex V and the to vertex W, the weight or the capacity C associated with the edge, and also the flow. So that's a flow edge. And then the flow network, since we're going to go through edges in the wrong direction, we're going to have to put every flow edge, kind of like an undirected graph, in both adjacency lists. And then we're going to test whether we're going, which direction we're going through an edge. It's kind of like using an undirected graph, but the flow network anyway has to have edges in both places so it can do backward edges. A simple way to arrange for this is to compute for the edges what's called the residual capacity. And that's just what we're going to use to compute the bottleneck value, the maximum amount of flow we can pull through. So for a backward edge, we'll assign the residual capacity to be the amount of flow, and for a forward edge, it'll be the capacity minus the flow. So that's the maximum amount of stuff we can get through the edge when we're augmenting. That's residual capacity. And to actually do the augmentation, you'll have a value which is your maximum amount that you're going to augment. And so if you're on a forward edge, you add it, and if you're on a backward edge, you subtract it. So that's the basic idea, and it's just quite natural from the graph representations we've been using and the way that the forward focusing algorithm works. So one way to think of this is a little bit closer to the representation that we're using, is to consider what's called a residual network. That for every edge, every forward edge in the network, it has the forward edge going that has the amount of flow left, and a backward edge with the amount of flow that's there. And if you have a full forward edge or an empty backward edge, then you only have one such. So this is an example of the residual network for this amount of flow. You can't put any more flow through from this vertex to this vertex, so there's no edge going that way, but you can remove 4 units of flow going that way, so that's because of the backward edge. And in this case, we have a full forward edge, so there's no edge going this way because we can't put any more flow through, but there's 9 going that way. That's another example of a full forward edge. This empty one, you can put 8 units of flow that way, so we have an edge in the residual network going that way, but no way to go that way because there's no flow, there's no backward edge. And so this network is just a natural way to look at the network while the flow is being computed, because it's a digraph that we're going to search in to find the augmenting path. You have a directed path in this network, that's from S to T, that's an augmenting path. And that's a simple mechanism that helps us write compact and elegant code. So that's an augmenting path in the original network, and that just turns out to be a directed path in the residual network. So then we can just use our algorithms that we've already studied for finding directed paths in the residual network. All right, so here's the API for flow edges, and they just have the few extra methods to allow us to compute and make decisions based on the amount of flow and capacity in the edge. These are the computations that we need to implement the forward focus and algorithm. So every edge has a from and a to. If you have one point, it gives you the other one, which we need just as we did in undirected graphs. Every edge has capacity and a flow and a residual capacity, which we compute from the capacity and the flow. And then we want to be able to add residual flow to any edge. And it gets added if it's forward, and it gets subtracted if it's backward. Those are the basic methods in the API for a flow edge, and the implementation of all of them is straightforward. Notice that one thing that's a little different from many other classes is that actually the goal of our computation is to fill in these values flow. So they're not final variables. That's what we're computing. Now we do it through add residual flow, but still it's not a final. So create an edge just with a V to W given capacity, just fill in the instance variables. And then all these other ones are just getters. Other is just like in an undirected graph. And then residual capacity and add residual flow are also easy to implement. So residual capacity, if it's on the from edge, you return the flow. If it's on the to edge, it's a backward edge, you return capacity minus flow, just as we said. And add residual flow makes the same test to decide whether to add or subtract the flow. So very simple implementations of all of those operations for our flow edges in a flow network. So what about the flow network API? It's again going to be our standard API, just that flow networks are built out of flow edges. And they're going to be built for the client, which is going to be the Maxflow algorithm, is going to have a method that gives an iterable for every vertex of all the forward and backward edges instant on that vertex. So that client's going to use these basic things. And given everything we've seen, this implementation is pretty straightforward. It's pretty much just like edge-weighted graph, except we use flow edges now. And then when we add an edge, even though it's kind of a directed network to handle flow and forward and backward edges, we add every edge to both adjacency lists. But simple code, quite similar to what we've seen before. Networks usually huge and sparse, so we use a vertex indexed array, and the entry associated with each vertex will contain references to all the edges that are incident on that vertex, whether they're forward or backwards. So just like an undirected graph, you'll have two references to the same edge, one in its from and the other in its to. And then rather than just a weight, they have a flow and a capacity. So from 0 to 2, it's got capacity 3 and 1 unit of flow in it. So that's an example of how to represent that edge. So flow network has got flows in it, that's the gray, and it's got capacities, that's the white, and otherwise it's kind of similar to our undirected graph representation. But when we're processing the graph, we use residual capacity to make it kind of work in the residual graph in the natural way. So this is the implementation of the forward focus and algorithm. And again, pretty straightforward to given the description that we've done and the graph processing code that we've written up to this time. So it's got have an array of vertices that we've been to. It's got an edge to array, which is the how do we get to each vertex so we can provide the client with the flow. So that we can process paths in the graph, and then it's got the value of the flow. So let's look at the code. It's kind of self-documenting. What we'll do is we set the value of the flow to 0. So we're going to find out if it has an augmenting path, and we'll look at that method in a minute. As long as it has an augmenting path, then when we call has augmenting path, basically what that's going to do is that's going to do a graph search and mark the vertices that it visits, and if it gets to this target, it's going to leave that path in the edge-to array in the standard way. The edge-to of T contains the edge that contains the vertex that took us to T and so forth. And so we'll use that edge-to to go back through the path and to figure out the bottleneck capacity, which is the minimum of the bottleneck capacity and the residual capacity in the edge that we're processing. So that's the maximum amount of flow that we can push through the network is go through the path and find the minimum of either the unused capacity in some forward edge or the available flow in some backward edge. So then once we have the bottleneck capacity, then we just go back through the path again and add residual flow to every edge in that path. So that's augment the flow. And then once we've augmented the flow, then we update the value. Notice that when this terminates, it terminated because we couldn't find an augmenting path. And we couldn't find an augmenting path meant that essentially we did a graph search that got stuck with finding all full forward edges or empty backward edges before getting to the target. And that's precisely the computation that we needed to do to compute the cut. So to tell whether vertex is reachable from S, we just check marked V, and so we can tell the client which vertices are in the cut, and then we can find the edges that leave that vertex to get the edges that comprise the cut. So now all we have to do to finish is to look at has augmenting path, which is the graph search in the residual network. And for this example, we'll use breadth first search, although the other search algorithms that we've studied can be adapted in the same way, depth first search, or using a priority queue as in Prim's algorithm or Dijkstra's algorithm. So we have our standard edge-to and marked arrays. And so we're going to have a queue which is going to contain the vertices that we've encountered but not yet visited. We'll put the source on there. While the queue's not empty, we'll take a vertex off. And so we'll go through everybody associated that's connected to that vertex. It's a flow edge. And then you check the residual capacity. And if it's bigger than 0, that means you have a way to get to W, and if it's not marked, you haven't been there yet, then you go ahead and go there and mark it. It's essentially breadth first search. So that's the code for has augmenting path, and that essentially completes the implementation of breadth first search. And mark T tells returns true or false. If you can get from T to S after that search is gone, then T will be marked and you can return true. This method can return true. That's the Java implementation of the Maxflow.